Hi all, let's discuss about gradient boosting. So first we have to import the required libraries like NumPy, Pandas for data manipulation and scikit-learn for machine learning utilities and matplotlib and seaborn for amazing visualizations. Next we load the diabetes dataset. So this dataset contains around 15,000 rows and 10 columns representing features like glucose level, BMI, age, whether or not the patient is diabetic, and inspecting the first few rows, which really helps us understand the structure of the dataset, which is there in the file. And then the first step is going to be data preparation, therefore separating features X and the target Y. We drop irrelevant columns like patient ID and isolate the diabetic column as our target. Next, we standardize features using standard scalar because scaling ensures that all features contribute equally to the model, improving performance and convergence speed. Finally, we split the dataset into training and test. We can use 80:20 split, therefore, which ensures that the class proportions remain consistent across both the sets. So, before building the model, let's explore the data because it's a crucial step in machine learning project. Especially EDA helps us understand patterns, distribution, and relations in the data. So these are the feature distribution graphs of various parameters. And then let's start with class distribution. It's actually important to know whether our data set is balanced or imbalanced. Here is the chart of class distribution of diabetics with non-diabetes patient. So let's move on to heat map. A correlation heat map helps us identify relationships between features. For example, high correlation between glucose level and diabetes could indicate its significance as a predictor. Building the gradient boosting model. So gradient boosting is a powerful ensemble technique that builds models sequentially, with each model improving upon errors of previous one. So we use 100% estimators for or decision trees with a learning rate of 0.1. Therefore, meaning each tree contributes 10% of the final model. The depth of the tree is capped at 3 to prevent overfitting. Once we are done with training, we evaluate the model using predictions on both training and testing sets. Therefore, accuracy gives us a quick overview of model performance. In this case, our gradient boosting model achieves 96% on training set and 95% on testing, which is actually a great result. So the confusion matrix provides a detailed breakdown of correct and incorrect predictions. It's especially useful in this kind of imbalanced datasets. The ROC curve evaluates the trade-off between sensitivity and specificity, therefore plotting it between true positive rate versus false positive rate. Basically, the area under the curve provides a single metric summarizing the model's performance. And also, the crucial recall curve are particularly helpful for imbalanced dataset. They show off the trade-off between precision and recall at different threshold values. One of the biggest advantages of gradient boosting is its ability to provide feature importance scores, helping us identify the most critical predictor. So, as you can see, the importance of the various features which are there in the dataset. So, moving on to residual plot helps us analyze errors made by the model. Ideally, residuals should be randomly scattered without patterns. And errors with versus iterations. This plot shows how model error evolves as more trees are added. A sharp decline indicates rapid learning in the initial iterators. cumulative gain chart. So cumulative gain charts visualize how well the model separates positive and negative classes. Higher curves indicate better performance. So let's move on to the lift chart. Basically, the lift chart complements cumulative gain charts, showing the relative improvement of the model over random casing. So finally, let's look at the distribution of predicted probabilities. This helps us understand how confident the model is in its predictions. That's all. Thank you.